Today, I'm going to tell you a story of one of the most important and amazing scientific discoveries of the last 150 years. And that is the discovery of what we call the cosmic background radiation. It's the strongest evidence we have for the Big Bang theory of how the universe began. Now, the currently accepted scientific consensus for the beginning of the universe is that it started in a quote-unquote explosion, or a vast expansion of matter and energy about 13.7 billion years ago. Now, people often ask me, how could we possibly know this to be true? Well, we don't know it to be true. What we do is we collect evidence, and then we see if the evidence matches reality. And for the Big Bang Theory in specific, the cosmic microwave background radiation is one of the strongest pieces of evidence we have. Now, what I get asked all the time is, if the universe started in an explosion, where is the center of this explosion? And the answer is, there is no center that you can point to in a given direction. And I need to demonstrate that to you. So this is a balloon. And on the surface of this balloon, I've drawn some dots. You can think of these dots being stars or galaxies. Now, what you need to do is you have to use your imagination. You need to pretend that you are an ant that lives on the surface of this balloon, but there is no inside the balloon to you. Your entire universe is just the surface of this balloon. You can go up and down and left and right, but you can't go inside the balloon because you only live on the surface of the balloon. Like we have 3 dimensions of space and 1 dimension of time. We live in this 4-dimensional space-time, 3 space and 1 time. We can't experience directly any other dimensions that might exist. Right? Now, if this is our universe and we live on the surface of it and a vast expansion happens very rapidly, notice how these dots are all getting farther apart from each other. Right? They're getting farther apart from each other. Now, if I live here, if I live on this planet and I look out in all directions, then I'm going to see stars this way and this way and this way and this way. And I'm going to ask myself, where is the center of this explosion? And the answer is that every possible direction it could be equivalently the center, because no matter where I live, whether I live on this side or this side or this side, or this, if I live over here, I see everything expanding away from me. If I live over here, I see everything expanding away from me. If I live over here, I see everything expanding away from me. So if I live on another star system nearby, I would look out and see all of the stars and galaxies moving away from me. Just like here, we look out. One of the biggest discoveries of the last 100 years, again, along with the background radiation, is the observation that all of the stars and the galaxies that we can see are all moving away from us. We can tell by the way the light is emitted from those objects that they're all racing away. But no matter where you are in the universe, you will always think everything is racing away from you, because we live in a situation where everything is expanding. It's not just that the stars exploded and made the universe. It's that space and time itself have been expanding for 13.7 billion years. So you can think of the distance between the stars here on the balloon as the space in our universe. So it's not just that things are getting farther apart, it's that space is being created, space itself is expanding. All right, so that's the prevailing theory. It sounds insane, it sounds crazy, but that's the best evidence we have for the universe we actually live in. And if we trace this expansion back, then about 13.7 billion years ago, everything was compressed into an infinitesimally small, we don't know exactly what it looked like, we don't have pictures of it, but some infinitesimally small, high-density region, which then undergrew. You can use the word explosion, you can use the word expansion, inflation, but it rapidly expanded, creating space and time in the process. Now, when the Big Bang happened, you know, all of the, you can think of it being a big mass of energy that's expanding, and some of that coalesced into matter that we know of today, and stars and planets. But you can think of photons flying around as being very high energy waves in the early universe. But as the universe expands, then those early photons, which were really, really high energy, they get stretched out so that, again, we're going to talk about exactly how it happened. Today, we look in every direction, and not only do we see all the galaxies moving away from us, but we see a constant background radiation at exactly the right frequency that we would expect to have originated with the Big Bang. Let me show you one little demo of that. These are simple little demos, but I think very effective. So here we have our universe, okay? In the early universe, here's a little photon, it's a little wave packet, right? Very high frequency, very, very tight wiggles, right? But then the universe begins expanding and expanding. For 13.7 billion years, it expands, and those photons, which were very tightly wiggled, now the crests and the troughs are much, much farther apart. So the very, very high energy photons in the early universe, 13.7 billion years later, they don't look like high energy photons anymore. They look like very low energy microwaves in a similar wavelength to the microwave that you have in your home. We look in the sky and we see microwaves everywhere. And by knowing the age of the universe, found by independent means, and knowing the energy or estimating the energy of the Big Bang in the content of the Big Bang, then we can predict how much, it's called redshifting, when the waves are stretched out from a very, very short wavelength right here to a very, very short wavelength to a very, very long wavelength. And we expect, if you do the calculations, you expect to look around in the sky and see this afterglow of the Big Bang. And that's exactly what we see. And so today, we're going to talk about the story and the results of the cosmic microwave background radiation, which is the leftover remnants from the origin of the universe. Now, for thousands of years, humans have looked up in the sky and tried to guess and hypothesize and wonder, how did it all begin? And for all of recorded history, which has only been several thousand years, the stars have looked exactly the same to us. We now know that the constellations change over time, but humanity as a civilization with written records hasn't been around for more than a few thousand years, right? Maybe 4,000 or 5,000 years. And so the constellations, they almost look exactly the same then as they do now. So it's very natural, about 100, 150 years ago, when people started writing mathematical predictions of maybe how the universe began, to come up with what they coined at the time the steady state model of the universe. That was the prevailing theory at the time. And the steady state theory of the universe, which very smart people subscribe to, even Albert Einstein subscribed to that for a long time, it basically says that the universe more or less doesn't change. Now, over small, very, very small regions of space, it can change. Stars can die, stars can be born, right? But if you zoom out and look at the entirety of the universe in general, it more or less looks the same. You have some stars dying, some stars coming into existence, but more or less, on the whole, it looks the same. It's not getting bigger, it's not getting smaller. It has always existed for all of time, and it will always exist more or less in the same way for all of time. That was called the steady state theory. But again, about 100, 150 years ago, scientists started putting together ideas. Maybe it wasn't always steady state. And some people put forth ideas from other observations that maybe the universe started in some high density region and then exploded. Now there's a whole, and I use the word exploded, but when you imagine an explosion, you think of something exploding into the surrounding space. Like if I think of some bomb exploding, I think of it rapidly expanding inside of the surrounding room or inside of the surrounding atmosphere. But when I say the Big Bang exploded, I mean there is no space outside of the Big Bang. The thing that you call space doesn't exist. And so the space is expanding and being created with the expansion of the universe along with the Big Bang. So the Big Bang is not just a creation of matter and energy, it's a creation of space itself and along with it, time itself, right? Before which there is no definition of space or time. So there were different scientists believe different things, right? And again, started looking in different areas of the sky and realized that everywhere we look, we see the galaxies receding away from us. And consistent with our little balloon analogy, that means that, that there is no center to the explosion because of what I talked about earlier, but at some point all of this matter and energy were concentrated in a much, much higher density of space, and something rapidly caused it to expand. The cause of that we don't know yet. I mean, science is all about learning over time. We don't know all the answers, but that is what we believe today based on the evidence that we have. Now, in parallel with this, I need to talk a little bit about electromagnetic waves. You see, when we look up in the stars, we see twinkly stars of visible light. But visible light is only a very small part of the electromagnetic spectrum. You have the visible light, and then you have, X-rays and gamma rays, very high energy waves on one end. And then on the other side of visible, you have infrared, and you have radio, and you have microwaves, which are the longer wavelengths on the other side. Now, all objects in the sky emit some emit visible light, like the sun, right? And Jupiter, you can see Jupiter in visible light, but you can also see that Jupiter emits radio waves. The sun emits radio waves. Pretty much every star also emits different frequencies, including microwaves and radio waves. So astronomers have used radio astronomy using very large radio telescopes to study the night sky for the better part of the last 150 years, ever since radio waves and electromagnetic radiation were ever discovered. One thing for you to understand that's critical is that whereas visible light is more or less in the center, when you have waves that are very much smaller in wavelength, higher frequency on one side of visible, those are very high energy photons. Those can damage you, like give you a sunburn, things like that, and also kill you. And on the other side, when the waves get very long, like radio waves and microwaves get very long, the energy of every photon is very low. So all of these waves are not all created equal. The very highly wiggly, high frequency waves have high energy, whereas the other waves on the other side, like radio waves and microwaves, very low energy in each individual photon. So let's fast forward to 1965. A scientist by the name of Penzias and his colleague Robert Wilson were using Bell Labs horn antenna in New Jersey, which is a very large, for the time, horn antenna, which is a 6-meter antenna. Now, this antenna was originally built to study the atmosphere. What they would do is float balloons up in the atmosphere, and they would shoot radio waves or microwaves off of the balloon, and then it would reflect off, and that they would detect it. These radio waves would bounce off and like echo off of the balloons, and from that you can learn a lot about the atmosphere, the upper atmosphere winds, and things like that. So they mostly used it for atmospheric studies like that. But it was a very sensitive telescope in the radio range and also in the microwave range. The other thing I'm going to say is look how physically large this antenna is. This is for two reasons. So you can collect as much energy as possible, but also because, see, they were studying radio waves and microwaves, which have a long frequency. If you have a very long frequency, then you need a physically large antenna to be able to catch the waves. So this is called a horn antenna, and it literally channels the waves into what we call a waveguide that goes into the receiver, and it's then amplified. All right, so Penzias and Wilson decided to use this telescope for a broad sky survey. Instead of looking at balloons, they would just point it at the sky and do very delicate measurements and just see what they would get. No matter where they pointed this antenna in the sky, they were getting a constant background noise at a very precise wavelength, 7.35 centimeters. And what I mean by that is the electromagnetic wave, one crest to one trough, or from when the wave begins to repeat, like from this distance here, all the way to this distance right there, 7.35 centimeters. So I'm not drawing it to scale. This is a little bit too big, but you get the idea. It's a fairly big wave. It's physically something you could hold in your hand. Although it's invisible, you can't see it, but it's energy that's being transmitted at that wavelength. Very low energy wave because it's so broad like this, okay? And they were seeing it everywhere, and it was very frustrating because they thought it was just noise. They were trying to do a sky survey, and they were getting this noise no matter where they looked. Okay, so over time they tried to eliminate this noise. They would make sure and do it at nighttime instead of the daytime to make sure the sun was not the source of the noise. They would make sure and do it when the moon was not in the sky because the moon reflects the sunlight, and to make sure that that wasn't a factor either. They would, if you've been out in the dark sky, you can see the Milky Way, the plane of the Milky Way galaxy that stretches across from horizon to horizon. They would look at this frequency in the plane of the galaxy, and then they would look off plane of the galaxy, and they would get exactly the same signal at the same amplitude no matter where they looked, to the sensitivity of their instrument. So then they began to think maybe there was something wrong with the receiver, or maybe there was something wrong with the telescope. So they went into the telescope and they discovered that there were actually pigeons nesting in this telescope because it's a very large structure. It's a horn antenna, and so things can fly in and out. And so they got rid of the birds, and they had a lot of bird droppings inside that could cause some interference. So they cleaned the antenna top to bottom, redid the sky survey, and they found exactly the same results. They had uniform radiation no matter where they pointed this telescope, and they became confident that it was not coming from the ground, it was not coming from the sun, it was not coming from the moon, it was not coming from the planets, it was not coming from the galaxy, either our galaxy or any other galaxy. It was simply something present everywhere, no matter where they looked, with, to the sensitivity of their instruments, the same intensity of this noise everywhere they looked at this microwave wavelength. Now, at the same time, at Princeton University, which is about 60 kilometers away from this independent group of people using the radio telescope or the antenna, we had other scientists who were doing theoretical calculations, working on this Big Bang model and kind of thinking about what would happen if a Big Bang actually had sort of happened. And they theorized that if we had very high energy waves that were emitted in the Big Bang, and if the universe really was expanding, just like our balloon, where space itself was expanding along with the distance between all the objects, that those early photons, if they were very high energy, should be stretched out into a longer wavelength. It was led by a scientist named Robert Dicke and Jim Peebles. They discovered when they ran their calculations that the frequency range that we should be seeing today, present everywhere, is right in the range of the centimeter wavelength range, which is the microwave range. So completely independent. They didn't know about these people doing measurements. They began to publish, preparing a paper for publication, and were beginning to do their own sky survey when they discovered that these other people had already done the survey completely independently for other reasons. So they began to look at each other's data and realize that what they had detected was not some weird thing with their instruments. They had detected the early afterglow of the universe. So when they used that radio telescope, that horn antenna, to look up into the sky and detect this noise, for lack of a better word, what they were hearing was literally the photons that had been created at the beginning of the universe, that had been traveling through space and time, and just like our balloon had been stretched out from the early emission from the Big Bang. And when they did their calculations and they did their survey, they determined that if you convert the frequencies that they were detecting into a temperature, what we call a black body temperature, it came out to about 2.7 Kelvin. Now, let me remind you that absolute zero is a theoretically lowest temperature anything can be at, and it is literally the lowest temperature when nothing at all moves. In fact, nothing can ever get to absolute zero due to quantum effects I'll talk about some other time. But 2.7 Kelvin is very, very low. Just for reference, liquid nitrogen is at 77 Kelvin, and liquid helium is at 4 Kelvin. And so anything lower than that is like exceedingly difficult to get to in a lab. We've done experiments very much colder than that, but getting down to 2.7 Kelvin is not an easy thing to do. Now, when we say the temperature of the Big Bang radiation is 2.7 Kelvin, what we're saying is that the frequencies that are emitted, if it were a single object emitting them, it would be a very cold object at 2.7 Kelvin emitting those frequencies, according to what's called black body radiation. I don't want to get into the details of that, but everything in the universe at a temperature emits radiation. So those very, very ultra low frequencies would be coming from something equivalently that's very, very cold. And that 2.7 Kelvin is in all directions. Now, we've had modern observations with satellites, I'll get to in a second, that show very slight variations over the sky, but it's basically 2.7 Kelvin in all directions. Now, an interesting fact is if you take an old school television and tune it to over-the-air reception to in-between channels, so you're looking at a static screen, a lot of that static that you're getting is from interference with the ground and ground-based terrestrial transmissions. But about 1% of all of the static that you're looking at on the screen, if you do that, actually is coming from the Big Bang from space through our atmosphere, and the TV is picking that up. So if you actually look at static on a TV screen, then what you are in part looking at is actually listening and looking at the early universe and the radiation left over from the Big Bang. Now, the early observations with the horn antenna was just one antenna. They would point it all over the sky. But in 1989, NASA launched the COBE satellite, the Cosmic Microwave Background Explorer satellite, which was a satellite in space that would look out into space with a very sensitive receiver in the microwave region to take a map of the entire universe, look in all directions, away from the Earth, away from the solar system, all directions, and measure very, very precisely what the microwave emission was coming from all these directions. And so here's a picture of the Cosmic Microwave Background Explorer satellite there. The different colors represent the variation in the microwave intensities, and there are different colors here, but it's important for you to know that 2.7 Kelvin is the equivalent temperature of this microwave radiation. The different colors here represents fractions of a degree Kelvin. And by the way, when I say 2.7 Kelvin, it's like 2.7 with some decimals after. It's more precisely known than just 2.7 Kelvin. But these different colors represent a map of the different intensities, but still, over the entire sky, it's only fractions of a Kelvin different. It's almost completely uniform in all directions. But still, by looking at the very slight irregularities in the microwave radiation in different directions, we can get a sense of what the early structures of the universe look like. Now, in more recent times, we've launched a newer satellite called the Wilkinson Microwave Anisotropy Probe. Isotropic means when something's isotropic, it means it happens equivalently in all directions. So anisotropic means variations in different directions. So the microwave anisotropy, it's a hard to say word, but anisotropy, it just means that we're looking for variations in all of the different directions, okay? So here's a picture of that, and you can see that it matches up with the earlier COBE data, which was much more coarse. This is a much more sensitive instrument, so we can see much more clearly the early variations in the early structure of the Big Bang, basically, is what you're looking at. So the variation in the microwave energy is sort of the early protostructures of the galaxy before real galaxies were formed, when matter and energy was just beginning to coalesce. It's sort of showing us where in the sky these different clumps of matter and energy started to coalesce. So you really are peering back at time to some very small fraction of time after the Big Bang occurred. Now, the Big Bang is just a theory, right? But it is a theory that we have a lot of evidence for. And this is not a video on all of the evidence for the Big Bang. I mean, this cosmic microwave background is just one small part of it. We can also use the Big Bang model of the universe to predict how the early elements in the periodic table were formed. And we can show that the elemental composition that we see of the universe is very accurately predicted by the Big Bang model of the universe. So it's not just this piece of data. There's a lot of data for the Big Bang formation of the universe. But when you go back to when time began, when space began, you might ask yourself, well, what happened before that? What happened before the explosion, for lack of a better word? And I would kind of propose to you that there is no such question. Because when you ask, well, what happened before, you're asking in time, what came before in time? But time itself was created during the Big Bang, along with space. We know from Einstein's theory of relativity that space and time are mixed with one another into what we call space-time. And so if space was created and expanded at the Big Bang, so was time. So before that, there was no time. It would be like asking, what is north of the North Pole? If you're standing at the North Pole, there is no such question as what is north of the North Pole. What is before the Big Bang doesn't really make a lot of sense. And lastly, we always want to know, how will the universe end? We knew that the universe has been expanding for over 100 years, and so it was natural to think that maybe gravity would slow it all down and then it would begin to collapse on itself and kind of like form a big crunch. Maybe it would go back into a high density state again and explode again over and over and over again, and kind of have a cyclical forming of the universe over and over again. And so that's kind of attractive. It's kind of a nice cyclical thing. But in recent times, I mean very recent times, within the last few years, measuring how the galaxies are actually moving away from us, they're not slowing down, they're actually accelerating. Let me say that again. Not only are the galaxies in all directions moving away from us, they're actually accelerating away from us. And so the universe is not going to slow down, as far as we know, and collapse in on itself. It will continue expanding forever. Now, why is the universe accelerating? Well, there's postulated theory called dark energy to explain that, but that's very, very new cutting-edge physics for another day to talk about. But it is a fact that we know the universe is expanding and accelerating and will not collapse in on itself. So I hope you learned something here. I find it amazing that something so accidental as, I have an antenna here, let's just point it at the sky, see what we get. And then you discover the remnant radiation left over from the beginning of our universe. Hope you learned something. Thank you. See you next time in the next one. Learn anything at mathandscience.com.